Hello, welcome back to our little corner on the web, where we hope to develop and nurture a love for math. Today, we have a super pahabol edition. Hopefully, some of you will still be able to use this in time for the PMO. But we'll go over the last two questions in part one of the 25th PMO qualifying stage. Okay, so I flashed them both here, questions 14 and 15 of part one. Uh, Question 14 is more of a counting/logic problem, I guess, and question 15 is in the realm of algebra. Okay, so feel free to pause here just to at least give them both a try before diving in. Okay, proceeding to question 14. Okay, question 14 asks, how many ways are there to divide a 5 by 5 square into three rectangles, all of whose sides are integers? Assume that two configurations which are obtained by either rotation and or a reflection are considered the same. Okay, so problems like this are the ones that you read a couple times and then you realize that, oh, this is doable. So when you see problems like this in the PMO, you want to be very careful and not give away points, right? So this one, because the numbers are also so low, turns out that we can just sort of draw them out instead of really applying anything else. So we know that the side lengths are integers. So the biggest that we can make is a 4 by 5. So let's start drawing from the biggest, rectangle that we have to the smallest one and see what happens. Okay, so if we have a 4 by 5, we can sort of cut our original first one like this, a 4 by 5, and a 1 by 1, 4 by 1. And the other one will just be, with a 4 by 5 at least, is a 4 by 5 and a 2 by 1. And it turns out that that's pretty much it for having a 4 by 5, right? If this was 4, 5, 1, 4, 1. Okay? And this is 5, 4, 1, 3, 2. Okay. Because the rest of the 4 by 5s are just reflections and rotations of these two shapes. So we end up proceeding to a 5 by 3. I'm gonna hopefully make my drawings a little bit smaller than that because it won't fit. So if we do 5 by 3, then the only cuts we have are one that goes like this. Another one that goes higher, where this is now 2 and 3, 2, 3, 5. Okay, and one that goes vertical. Oops. Okay. So it turns out again that those are the only cuts where the left side is a 5 by 3. Okay. The rest you can sort of show are just rotations and reflections of these two. Oh, those three. Okay, so we proceed to 2 by 3. 2 by 5, sorry. 2 by 3. So 2 by 5s. And again, we follow the same pattern first. We do the one that are with horizontal line. Okay. So this is 2 by 5 and then 1 and 4. And the next one, 2 by 5. So this again, 2 and 2. The rest are sort of obvious, hopefully. And then we do the verticals. The verticals, we have 2, 2, and we have the flips. We have the 2, 1, 2. Okay. Turns out again that those are the only ones with a 5 by 2 on the left-hand side. Okay. So the last one is to go deal with the 5 by 1 on the left-hand side. So same pattern, we do that. This. Okay, so this is a 1, 1, 4, 4, 1, 4, 2, 3. And then we have the verticals. 1, 1, 3, 1 in terms of lengths. And the only one you actually had to be careful with, if you try to draw this, I'm going to draw it in red so that it's clear. You want to be careful with, with drawing this guy. This might be the only one that might trick people if you try to draw it. A 113. The reason I say that this is the tricky one is 113, if you really carefully look, it's actually the same as this guy. Okay, so if you go smaller and smaller, you have to cross-check that, have I drawn this before? And that's the only one. So even if you actually drew that and sort of got stuck, you will see that you had 13 drawings, which means that there's something off because there's no 13 in the choices, right? So hopefully that made you cross-check. So that's the only one that I found to be a little bit tricky in trying to draw these things. But that basically results in the final answer being 12. There's 12 shapes we've drawn that has no repeats, whether rotation or reflection. Okay, so moving on to the next question here. Question 15 asks, let a sub 1 be a positive integer less than 200. Define a sequence a sub n by 3 times a sub n plus 1 minus 1 is equal to 2a sub n for n greater than 1. Let a be the set of all indices m such that a sub m is an integer, but a sub m plus 1 is not. What is the largest possible element of a? So what this really means, if we start up with some integer, let's call it I1, then when you run it through that relationship, you will have I2 is still an integer, I3 is an integer, and I sub m is still an integer, right? But m plus 1 is no longer an integer. So we are trying to look for this largest m. Okay, so let's try to find a pattern for how we can write an. So the only thing we know right now is a sub 1 is less than 200. Okay, we can try to write a sub 2 in terms of a sub 1. Okay, just to, again, find a pattern. A sub 2 is 2a sub 1 minus plus 1 over 3. And then we try to write again more and more just to see if we can find a pattern. This will be twice a sub 2 plus 1 all over 3. We plug in a sub 2, or what we know of a sub 2. A sub 1 plus 1, 2. Sorry, I missed the 2 all over 3 plus 1 all over 3. Expanding a bit, we get 4a sub 1 plus 5 all over 9. Okay, I distributed the 2 and multiplied by 1 over 3 for this guy over here. So a sub 4 is, again, 2 times a sub 3 plus 1 all over 3, which is twice of twice of 4 a sub 1 plus 5 all over 9 plus 1 all over 3. If you simplify that, you get 8 a sub 1 plus 19 all over 27. Okay, so here's where I sort of paused a bit and said, is there a pattern that I can sort of take advantage of? And if you've solved integer only solutions, this might look a little bit familiar. you see that the 19, I can sort of make a 27, and the 8 that I will add or subtract matches the other 8. So we can write this as 8a sub 1 minus 8 plus 8 plus 19. Okay, let's get rid of that. Plus 19. We end up that we can simplify that as 8 times a sub 1 minus 1 plus all over 27. And then we just get a plus 1. So we go backwards and say, can I do that with the rest? It turns out we can. So this is 4a sub 1 minus 4 plus 4 plus 5 all over 9. This turns out to be 4. Okay. 4 times a sub 1 minus 1 all over 9 plus 1. And the first one is also can similarly be written as 2a sub 1 minus 2 plus 2 plus 1 all over 3, which is equals to 2 of a sub 1 minus 1 all over 3 plus 1. So the pattern actually holds. So a sub 5 can simply be written as, if you notice also, it's 2 squared, 2 cubed. So a sub 4 can simply be written as 2 to the 4th times a sub 1 minus 1 all over 3 to the 4th plus 1. And a sub 6 can be written as 2 to the 5th times a sub 1 minus 1 all over 3 to the 5th plus 1. Okay, so if a sub 1 is an integer, then for a sub 2 to be an integer, a sub 1 minus 1 has to be divisible by 3 because 2 is not divisible by 3, right? So here, a sub 1 minus 1 has to be divisible by 3. And then for a sub 3 to be an integer, a sub 1 minus 1 here has to be divisible by 9. For a sub 4 to be an integer, a sub 1 minus 1 over 27 has to be divisible by 9. And for a sub 5, it's the same thing. It has to be divisible by 81, right? A sub 1 minus 1. And for a sub 6 to be an integer, it has to be divisible by 243, which is 3 to the 5th. But we know that a sub 1 is less than 200. So a sub 6 is not possible. So we only know that a sub 5 can be, because 3 to the 4th is 81. So if 81 divides a sub 1 minus 1, we're good. And there's two possibilities, actually. We're not asked for it here, but there's two possibilities for that. A sub 1 minus 1 can be 81, or a sub 1 minus 1 is equals to 162. So we have two possibilities for a sub 1, which is 82 or 163. So if we started with those, as a sub 1, we should be able to get to a sub 5. That's still an integer, but a sub 6 will no longer be an integer. Okay, so the answer here is A5. Hopefully, these solutions are helpful and educational. If you found them so, do hit the like button and subscribe. Again, good luck for those taking the PMO later today. And all you can control is your preparation. So hopefully you prepared well. Thanks for watching.